This is Ryan along with Amitesh,
Hello.
Kang,
Hey there.
and Tristan,
Howdy.
and we will be discussing our research on microwave filters. Throughout this presentation, you will get to know about what a microwave filter is, the history and theory behind it, the various types of microwave filters, and more specifically, the band and planar filters, and finally, the practical applications of microwave filters. Not to be confused with convection ovens, microwaves are a form of electromagnetic radiation. The term microwave refers to the size of wavelength in comparison to other wavelengths, rather than the wavelengths being in the micro range. Microwaves have the second largest wavelength in comparison, with only radio waves having bigger. Microwaves operate in the frequency range of 300 MHz to 300 GHz, and their wavelengths range from 1 millimeter to 1 meter.
For what is a filter? First of all, a filter is a device that is used for suppressing electrical or sound waves of frequencies that are unwanted in a wave signal. So that is the common functionality of a regular filter. By getting rid of the unwanted frequencies, a filter will help enhance the various frequencies that get through and are wanted. The various types of filters include the bandpass, bandstop, low pass, and high pass filters. Now, the various functions of each of these filters include, let's start with first, the bandpass filter. The bandpass filter selects a desired band of frequencies, which range from one limit to another. A bandstop eliminates undesired band of frequencies, whereas a low pass only allows frequencies that are below a cutoff frequency range, whereas a high pass allows frequencies that are above a cutoff frequency range. Usually, microwave filters are bandpass filters.
Microwave filters. Microwave filters were first researched prior and during World War II due to the influx of radar systems being used. Notable research was conducted at big laboratories such as MIT, Harvard, and Bell Labs in the 1940s. The work at MIT produced narrow band waveguide filters that was used for radar systems, and the work at Harvard produced variable waveguide filters. This research paved the way for future discoveries in the field of electromagnetics.
Alrighty there, now let's do a bit of theory for the microwave filters. A filter that functions under microwave frequencies is known as a microwave filter. Microwave filters absorb most of the signals such that very little signal is reflected back, which makes them very unique. A microwave filter has a low mass, low volume, as well as very high resistance to various temperature changes. It also performs the same functions as electrical filters, but at lower frequencies, and has a different implementation than an electrical filter, which we will talk about later on in this presentation. Microwave filters can also combine or separate multiple frequency bands, and that is therefore the theory of microwave filters.
Types of microwave filters. There are many types of microwave filters, and I'll go through a few of them right now. There's the lumped element LC filter, the planar filter, the coaxial filter, cavity filter, dielectric filter, and electroacoustic filters, just to name a few. I will go into detail for a few of them right now. So firstly, we have the lumped element LC filter, which is one of the easiest to implement, and is made from an LC tank circuit. These filters are compact and simple, but have the drawback of having poor performance. Secondly, there's the cavity filter, which is mainly used in the 40 to 950 MHz frequency range. The cavity filter is ideal for microwave filters due to the small size and increased quality in comparison to the lumped element LC filter. Thirdly, we will talk about the planar filter, which we will discuss later on in the video.
Now for how band filters work. As we know, different elements of a filter operate on different frequencies. Example, capacitors and inductors. We know that for a capacitor, when there's high frequency, it is short-circuited, and when there's low frequency, it is open-circuited. Whereas for an inductor at high frequency, it's open circuit, and at low frequency, it is short-circuited. For band filters, which are the most common type of microwave filters, they work at a limited range of frequencies. So as a result, it is hard to achieve high frequency values when using capacitors as well as inductors, as again they work at low frequencies. A high bandwidth is also achieved with band filters, so that only for a certain range of frequencies, because then not much of a flexibility is given in choosing what type of frequencies you're able to have. Also, in order to create a microwave filter that gets rid of these disadvantages that I've just stated, what we use is a different type of filter, and that is called a planar filter. And what planar filters are that they're made from distributed elements, unlike band filters, which are actually lumped elements. And what this difference does is that because of this, we are able to use microchips, which planar filters use. And what's so great about using microstrips is that in order to get rid of the disadvantages that a band filter contains, because when connected in series, microstrips act as a capacitor, whereas when in parallel they act as a inductor. So as a result, what these microstrips allow us to do is that they allow us to achieve high frequencies that we would not be able to with a band filter, as well as because they're not lumped and they're distributed, the frequencies, the signals don't concentrate at a one point, whereas for a band filter they do concentrate it, because again a band filter is dependent on just the time as it is lumped, whereas a planar is dependent on time as well as frequency, so making it having the characteristics of distributed elements, which makes it a lot better to use rather than a band filter for achieving high frequencies for a microwave filter.
Uses of microwave filters. We use microwave filters every day, and you might not be aware of it. Here are some examples of microwave filter applications. Broadcast radios, for sending communication signals through long distances. Television, sending television broadcasting to local homes. Cell phones, cell phone signals for communication. Wi-Fi routers, used in our house to provide us wire-free internet service. Radar or satellites, to help us locate things at different ranges. And noise-canceling headphones.
OpenEMS is a free open-source FDTD solver. It is very efficient when working in the Cartesian and cylindrical coordinate systems. A component that we will be using for modeling purposes is a C++ library called CSX-CAD. CSX-CAD is also used for deriving the geometrical models and their physical properties. There are various steps associated with the simulation process. First of all of the parameters that define the type of simulation, such as the boundary conditions and the number of simulated steps, are saved in the FDTD object, and the parameters for the geometry are saved in the CSX CAD object. Secondly, the properties of the structure being simulated must be defined. These properties include the physical properties such as materials used and non-physical properties such as probes. The primitives take the non-physical properties of the scattering objects, field sources, and field dumps and assemble them as objects such as curves and polygons. These are then stored in the CSX CAD structure. During the simulation, it is important to define all of the physical constants that must be imported in the units of choice, the material properties. The excitation must also be defined. This is the input signal that the structure receives. In fact, there are two types of excitation types: sinusoidal and Gaussian, and we must decide which one to use. As a result, we must declare the microwave filter's waveguide range within the program, set up the FDTD parameter and excitation function, the input function, and we will use the CSX CAD structure to create the model of the simulation once it receives an input using the excitation function.